so again, sample exam 3, 38 to 45. And starting with number 38. We have the E here is the error for the polynomial t of x, which is a Taylor polynomial. And it's approximated by x minus x cubed over 3 factorial. And you go to the slides.
I got it.
Alright, so bottom line is if we are using this polynomial at 0 to approximate the sine x at 0.5, the question is which of the following is true. So keep in mind that with the polynomial and with our actual function sine x here, okay, we could find the error, of course, just by putting in the two functions here and seeing what the y values are and comparing them. So if we take our x minus x cubed over 6, or sine x, and do our table set 0.5s. Looks like our two values here at 0.5, so t of 0.5 is 0.47917. F of 0.5 is 0.47943. So the actual error here, if we subtract those two, 0.47943 minus 0.47917. So maybe 0.00026 be the actual error. Right. And so knowing that we can certainly find the actual error, because we can evaluate both of those at 0.5, it's a calculator problem. The question then is where does that error fit into one of these ranges here? So ultimately, if we look at the range for the first one, it says that the absolute value of the error is less than 0.001. So if I compare this with 0.0001, okay, is my number less than 0.001?
No.
Okay. If you look at part B here, is it between 0.001 and 0.003? Yeah, absolutely. If I were to put that in between those two, that definitely would fit in between. And you notice the other choices are all of larger error than what we got. Okay, and keep in mind that that a function like this has an error bound, and that we could find, and ultimately the error that we get should be less than this particular error bound. Okay. So we didn't actually calculate the error bound. We really don't need to in this problem, but ultimately there is an error bound, and we know that if we get the error that we get should fit into one of those 5 categories, and of course it does fit into B. So it's definitely a BC problem. And so that's it. Questions on that one? Next. Oh. 40. We have a function, and that function is x cubed minus 7x squared plus 25x minus 39. So that being our function, it says that let g be the inverse function of f, and we want to know what is the value of g inverse or g prime at 0. Keeping in mind that g again is the inverse of this. Now, if we tried to actually find g here, we'd have to let this be x and these 3 be y, and then somehow solve that for y, which is virtually impossible and unnecessary. We don't need to do that. But bottom line is, remember the relationship that we need to know between inverses of functions and their inverses. Say just take for instance these two. These two are inverses of each other. If we have, if this one contains the point, let's say AB, and this one contains the point BA, which all inverses would have that feature. When one contains point AB, the other one would contain BA. Question is, what do we know about the derivatives at those corresponding points? Okay. Well, the way I drew it here, they look like they're somewhat parallel, but they're definitely not. The relationship is that at corresponding points, F inverse have reciprocal derivatives. Alright, so ultimately if we knew something about the derivative of our f function here, that might give us some insight as to what the derivative of g is at that particular point. So if we find the derivative of f, we'd get 3x squared minus 14x plus 25. True? Now keep in mind that what we want here is we want the derivative of g at 0. Okay? So keep in mind that the point in question here that we're worried about in terms of finding the derivative at this particular point is the point 0 something on this g function. True? So keep in mind the corresponding point that we're after here though, that on the f function would be the point what? If we're interested in the point 0 something on the g function, then we're interested in the point something 0 on the f function. And those are the corresponding points where the derivatives have a relationship. Okay, they don't have a relationship necessarily where they both have x equals 0, because those aren't necessarily corresponding points. Okay? So ultimately we need to figure out what is this. So basically what do we need to do with this? We need to set it equal to 0. We need to find the zeros of this function. Okay? And then find the derivative at that point. Actually I lied. We need to find the zeros of this function right here, the top function. So we need to know when f of x equals 0. So if we find that corresponding point, I would spend absolutely no time doing the algebra to figure that out. True. So I'm just going to do the take a graphical approach to find that point. We got x cubed minus 7x squared plus 25x minus 39. If we graph that, we can see that we have looks like 1, 0 here. Calculate the looks like 3, and we can verify that of course by putting a 3 in there and seeing that does equal 0 in fact. So that means that the point in question then is 3, 0. True? That means that on the g function, we now know that the point is actually 0, 3. Now, it's really irrelevant. We don't really, that's not really going to change anything with knowing that that's the fact, but it is. But bottom line is determining the corresponding points here where for g, the 0 is x, and for y, for the f function, is our 0. That means that these two would be the corresponding points for these two inverses. So bottom line is, if we knew the derivative of f at 3, 0, then we would also know the derivative at 0 for the g function. So bottom line is, if we put our 3 into our derivative that we found, what are we going to get? 27 minus 42 plus 25. So we'd ultimately get negative 15 and positive 25. That'll be 10. And so if our derivative of f is 10 at the point in question, corresponding point on g, our derivative better be 1/10, which corresponds with letter C. Right. So again, the key piece of information here is that when we have inverses, that at corresponding points, the derivatives of the two functions are reciprocals of each other. So if we can find the derivative of one at a particular point, then the other one's derivative at the corresponding point is going to be the reciprocal. And ultimately that's a AB topic. Derivative versus. Any questions on that one before we carry on? All right, next. Sure. 39, we have how many relative extreme values does the function whose derivative is given by y equals sine ln x have in the interval 0 to 1? So we have our differential equation here ultimately. And we have sine of ln x. We're only interested in the values from 0 to 1, not including 0, notice. And the question is, how many relative extreme values does the function have whose derivative is this? Okay, so we don't really need to know the function necessarily, we just know the derivative. And ultimately, what do we know about extreme values? Extreme values are going to occur when the derivative equals 0, or when the derivative doesn't exist, or when we have endpoints. And there is one endpoint on this, there's 1. So 1 would be a candidate here for our extreme value. And the other ones are where the derivative equals 0 here. Now, looking at our function that we have here, can the derivative equal 0? Well, let's see. If we're between 0 and 1, keep in mind that the natural log function between 0 and 1 looks like this. So ultimately, we're going to be putting in numbers here that are less than 1. True? So we're going to be taking the sign of values that are less than 1. And keeping in mind also that we can see this because it's a calculator problem. So if we do sine of natural log of x, and say we just go from 0 to 1, keep it at negative 10 to 10 there. Again, we went from 0 to 1. We can see that there is a 0 there. True? So let's test it and see what we get here. So if we do our 0 command, it's ultimately, again, this is the derivative, so where the derivative equals 0, we have an extreme value. We have a critical point, that is. Doesn't necessarily mean it's maximum or minimum, but in this case it looks like it is, of course, because it goes from positive to negative. So it looks like 0.043. And then over here, it looks like maybe there's another one possibly. So if we, I'm going to zoom in on that area over there by 1. See what we see here. Maybe there may or may not be another 0 over there. And it looks like when we do the zoom, it looks like the 0 is on the other side of 1 or at 1, or let's find out. You know, ultimately, we kind of know the answer already because natural log of 1 is 0, and sine of 0 is what? 0. So really, don't we already have that as a candidate, though, the 1? Okay, so ultimately, we're not getting another candidate by doing that. So the question is, looking back at our original, and looking at our derivative here going from negative to positive here, okay, what does that tell us? Is that 0.043, is it in fact an extreme value? Yeah. Okay. And the question is, what about 1? Is 1 an extreme value? Well, think about the derivative is what? Actually, let me change my window again. Actually, see the right window here. All right. So ultimately, I said that backwards. The derivative is positive, then negative. So ultimately, again, the function itself would be positive and negative. That means it would be a maximum at this 0.043 point. And then over here, the derivative is, keep in mind, negative the rest of the way. So ultimately, it would be decreasing all the way to get to 1. So could 1 be considered a minimum value? Or it's included in the interval, so it's got to be part of the analysis. So yeah, it would be a local minimum because it's the smallest point in its area because it's an endpoint. We don't count 0, of course, because of the fact that 0 is not part of the domain here. So ultimately, it appears that the answer should be B, correct? But I said E, so let's think about what might be happening here, where it's not, in fact, 2, like we think.
Undefined area.
Ultimately, is there undefined areas here? And keep in mind that the domain of the natural log is all real numbers greater than 0. So, not including 0, everything in our domain is good for the natural log. And ultimately, does sine have any domain issues? So the domain is all real numbers also. So any of these natural log numbers that I get after putting an x into the natural log, I should be able to get a sine value for it, shouldn't I? So I guess the question is there something that we're missing here in this picture then?
No.
There's something that we just missed, isn't it? So by zooming in, we just found another one, didn't we?
That's unfair. That's really unfair.
Oh.
So
So that still doesn't answer our question though, because it still appears that there's now just 3, right?
who knows? There might be hidden everywhere. Can't really tell.
So
More.
so if we do another zoom, let's see. I
Why not?
don't know if we'll see more on this zoom or not, but looks like just that one.
Maybe it's like this. Maybe it's on the other side.
Yeah, I'm trying to think of where another would be.
It's closer to 0. He said zooming in.
Is it even closer yet?
Yeah.
Keeps coming back. Let's think about why though. You know, and I don't know if I'm still on Zoom or not here.
Oh my god. Oh, okay. Yep.
Yeah. Ultimately, if we kept doing this, we're going to see that there is in fact more. Let's see if we could have predicted that without having to look at the graph. Right. Keep in mind, we're interested in when does this equal 0, right? When does the sine of the natural log of x equal 0? That's what we're after, right? Okay. We know that one of the answers here is 1 because that sine of 0 would be 0, wouldn't it? Okay. Think about why that my argument here being the natural log. True? Just think about it, as I go backwards from 1 to 0, okay, what kind of y values is that going to produce? It's going to go to infinity, isn't it? Think about what that's going to do for our sine function. Okay. As my y values, and as I'm going from 1 back towards 0, right? Okay. Ultimately, all the y values that are hit aren't at some point, aren't we going to hit negative pi? True. On the way to 0, aren't we going to hit negative pi? Aren't we going to hit negative 2 pi? Aren't we going to hit negative 3 pi, 4 pi, 5 pi, so on? In fact, really, how many are there altogether? There's an infinite amount, aren't there? As I approach those, I'm going to get my y values are, like I said, my y values, where I'm going to hit every y value to negative infinity. True? And what's on the way to negative infinity? Negative pi, negative 2 pi, negative 3 pi, negative 4 pi, negative 5 pi, and so on. So ultimately, that's why the answer is more than 4. In fact, there's an infinite amount, isn't there?
Pretty sure everyone would have got that wrong.
Yeah, maybe.
How
So.
do you think about that? Like, oh, 2 is in here.
That's what you got to be careful about, especially if you have time. Now, I wouldn't suggest necessarily for this problem. I mean, I would make sure that if I was going to spend just more time thinking about that I would do the other problems first and come back to it. If your initial guess is that, if you end up having extra time at the end, I'd look at it over again, especially if you're taking. One of the things that you just don't want to do is just take the graph's word for it. Right? You can avoid doing that. Okay? I would avoid that. Okay? Sometimes what the graph shows is correct. Okay? But ultimately, in this case, not so much because the infinite amount of zeros here going back and forth. It's, I guess another giveaway too is that since the sine's a periodic function, might be more than meets the eye. Okay? So like I said, I would just be careful with just looking at the graph and saying, oh, it's 2, see you bye. Probably not that easy. True? So like I said, especially if you have more time, think about what's going to happen with that function. What are we putting into the net? What are we putting into the sine function? Knowing that the sine could be 0 and infinite amount of x values that we put in there, that might give us some insight too. You know that the natural log as we go from 0 to 1 is going to get every y value. Right? And remember, the y values are the x values that we're putting in. The y values of the natural log are what we're putting into the sine. All right. Good question. I like that one.
I don't.
Very good one. All right. What else?
Well, they're all gonna be okay.
Fair.
41.
On 41, we have a differential equation, dy dx. This would be an AB problem too, by the way.
Oh, cool.
Be even easier for you. So xy minus y squared. They give us an initial value here, and it would be nice if we could actually find the solution to this. If we try to do separation of variables here, if we try to factor out a y, we would have y on the outside and then x minus y on the inside. And ultimately that would be an issue for us in terms of getting the separation part. I mean, if we did that, and again you could try to do that, but ultimately we want to get the y over there, but ultimately this side would have a y in it, which we wouldn't be able to get rid of because we'd multiply by dx and so on. So this really isn't, it's not a separable differential equation that we know how to solve. But keep in mind again, this is a derivative of some relation, right? And ultimately what we want is to come up with just a value here. Essentially, we want the value of y at 2. So the question is, do we have any other alternatives then to see if we could figure out what y of 2 equals approximately? So what are our options after we recognize that the differential equation is not algebraically solvable? Graph what?
Graph and something.
So what something would that be though? Not all differential equations are separable, so our only options at this point then to get an approximation here would be to use a slope field or use Euler's method. So if we used Euler's method, we had one of these the other day, remember? We ultimately have our initial point here as 1, 3. Right? And so if we do our 1, 3, and I guess what I would do if I were you, since you have a calculator here, is use your Euler's method program in your calculator. Probably the quickest and easiest way, and you would do it by hand. So if we remember, to use the Euler's method program, you need to put the differential equation into your y equals. So you got xy and then minus y squared. And then if we go program, you can do Euler graph or Euler table. I'd use Euler table because we don't really need to see the graph of it necessarily, if we want to, but if we do Euler table. You could use improved Euler's table too, we have that as well. But either way, our initial x here is 1, our initial y is 3. Step size, say we go by 0.1s. Number of points then would be 10 because we're only going to the y value, the x value of 2. And again, we're getting an approximation for each of these values as we go. Again, we could do all this by hand, but that would be a pain in the neck to do this 10 times, and not to mention time consuming. And ultimately we get 1.7289, which that does not compute. So let's figure out why. It's supposed to be -3, huh? There's a problem with my program. Did you you guys get the same thing for that program?
Yeah.
Let's try to improve it once and see what happens. 1, 3. I get the same thing with improve too, so something's not right. Xy minus y squared. Something's not right. Let me mess around with that again later and see if I can figure out what's wrong with the program, or if we're doing typing something in wrong. Let's try it. I'm pretty sure you just use the regular y's in that program. I don't remember doing anything different than that, so. We'll put that one aside for a minute. We'll revisit that later. Let me look at that. See if there's something with the program I need to fix or something. That should be a viable way to figure out what f of 2 is. That's what we want, is f of 2, right? Alright, well, let's move on to a different one, then we'll come back to that one another time. Jake. 42. In 42, we got a rectangle that's inscribed in a semicircle, has a radius of 8. And it's we go 8 in all directions here. There's our semicircle. And it says the rectangle is inscribed in the semicircles. Oh, we got some rectangle in there. Let's draw it in some random location here. Lying on the diameter of the circle, what is the maximum possible area of the rectangle? So ultimately, if we want to maximize area here, we just need length times width. That's our formula for what we're trying to maximize. We're trying to maximize the area of a rectangle. And we can't maximize that right now because we have two variables. Ultimately, in our picture, the way I've drawn it, the dimensions here for the length would be 2x. And the question is, can we come up with an equation here for the function, because this right here would be the y value, or the width. So the y value here would just be y equals square root of 64 minus x squared. That's our equation for a half circle. Alright. And ultimately, if that is our a function that we want to maximize, we want to find the maximum area here, then we need to find the derivative and find the critical points. So ultimately, in terms of finding the derivative, can't find it at a point. We have product rule problem here. So if we go 2x, and the derivative of the square root is 1/2 times 64 minus x squared to the negative 1/2 times negative 2x. Plus 64 minus x squared times 2. So, if we simplify then this stuff, we'd have these 2's would be gone. We still have a 2x, would be negative 2x squared on top. And square root of 64 minus x squared on the bottom. Plus 2 radical 64 minus x squared. Right, and ultimately we'd want to put these two together because we want to figure out when does this derivative equal 0. So if we put this together, multiply by 64 minus x squared over 64 minus x squared, both the square roots. And if we get our common denominator here, we're going to wind up with the square root of 64 over x squared on the bottom. And on the top, these two would cancel each other out in terms of the radical part, so we'd ultimately have 2 times 64 minus x squared, which would give me 128 minus 2x squared, negative 4x squared plus 128 on top. And other than that, if we want to figure out when this equals 0, if we set the top equal to 0, we're going to get 128 equals 4x squared. We divide, we get 32 equals x squared. Square root of 32 would be 4 radical 2. It would normally be plus and minus, but here x represents a length. So with that, the question says, what is the maximum possible area of the rectangle? Well, keeping in mind in our picture, if x is 4 radical 2, then the whole length would be 8 radical 2. Because there's x on either side of the origin here. And then the y value here, if we plugged a radical 32, which is our answer ultimately, into here, we'd get just 32. So it would be 64 minus 32 here to get our height, if you will, our width. So we'd have radical 32 in the parentheses. 4 radical 2 would be our height. And we get 32 times 2, which is 64. So again, that's AV problem. It's a maximization problem. Okay, questions on that one? What else? Open on the last three.
I did 43.
And 43, we have piecewise function f of x, e to the negative x plus 2 ax plus b. It's less than 0 here, greater than or equal to 0 here. So we have a function that's an exponential going into a linear. And the question here says let f be the function defined above where a and b are constants. If f is differentiable at x equals 0, then what is the value of a plus b? So ultimately we need this to be differentiable. So think about what it would take to make this differentiable. First thing that would have to happen is we know that this e to the negative x plus 2 function is going to be going through at 3, so it's going to look something like this. Because e to the negative x normally goes through 0, 1, but it's up to translation. And then we need our function, our linear function, not only to meet here and have a limit. Okay, so not only has to have a y-intercept of 3, that's already one answer then, isn't it? The b part. The b here has to be 3. So we can determine that by determining the y-intercept of the original function. Okay. All right, and then the a part here, again, to keep in mind, again, if there's going to be a derivative at this point, not only do they have to have a limit here, of course, okay, but the derivative on the left and the derivative on the right have to be equal. Okay. And ultimately, the derivative on the right is a. True? It's linear. So how about the derivative on the left? If we differentiate here, we're going to get negative e to the negative x, aren't we? The left-hand side. And if we put a 0 in there, we get what? We get negative 1. So ultimately, this is our f. This is our f prime at 0, point in question. So that means that if the curve is coming down here, and at that point right there, the slope of this curve is negative 1, what does the line slope have to be in order to stay on that same path and actually have a derivative there? It's got to be negative 1 also. Okay. So with that, we'd know that a equals negative 1, and so therefore what's b plus a? Equal 2. Key element of a piecewise function, if it's differentiable at a particular point, okay, the derivative of the left-hand side and the derivative of the right-hand side at that point, they have to be equal. Okay. So to be continuous, the y values have to be equal. To have a derivative, the derivatives have to be equal. What else? Sarah? 44, we've got another differential equation problem here. This time our dy dt is 2y and then t and t plus 2 here. And it's for t greater than 0. It gives an initial condition of 1, 1. And ultimately we want to know when t is 2, what is y. So in terms of separation here, if we do the 1 over y dy over here, and we do the 2 over t and t plus 2 here dt. This one we could separate the variables. And if we do that, then we can anti-differentiate both sides here. We get ln of absolute value of y here. And then over here, we need to figure out how do we find the derivative of this? Well, should be, hopefully when you see that, you should be thinking partial fractions. So you got a factored bottom. Okay. So ultimately, we need to do the partial fraction work for that. So we'd have t plus 2, a here, b here. I'd also factor the 2 out of here, move that out there for the time being. So it's really just a 1. I guess you could leave it as 2 really, because we could just equate it to 2, and I guess it really doesn't matter. You can do it either way. So let's not do that. We'll just leave it as 2 just for argument's sake. Alright, and so with that, if we were to add these together, we'd have to go b times t, and then a times t plus 2. And ultimately we want that to equal the top coefficient, which is 2. So we'd wind up with bt plus at plus 2a. So b plus a t plus 2a equals 2. And then our system would be b plus a equals 0, and 2a would equal 2. So a would be 1, b would be negative 1. So if we do the partial fraction work on that, then we'll set up a new integral here, 1 over t plus negative, and I'll just put a minus out there instead of a plus, so minus 1 over t plus 2. And integrating, natural log of absolute value of y would equal natural log of absolute value of t minus natural log of absolute value of t plus 2 plus c. And knowing that these are all 1s here in terms of our t's and y's, they told us the initial condition is 1, 1, right? So we'd have the natural log of 1, which is what? 0. Natural log of 1 here is 0, minus natural log of 3 plus c. So ln 3 would be our c value. So going back to rewrite, right there would be our equation. Not solve for y at this point. We could certainly compose both sides with e and solve that for y if we wanted to. And again, you don't necessarily have to, I guess, but bottom line is we just want to know what's y when t is 2. So if we were to put a 2 in there, we'd have ln 2 minus ln 4 plus ln 3. And keep in mind that we could use our laws of logarithms here on this one. We'd have ln of half, if we put these two together, 2 over 4, plus ln 3. Putting those together, we'd have ln 3 halves equals ln y. And now, once we have it in that form, I'd compose both sides with e, and we'd just get y equals 3 halves. Hopefully that's an option. And it is, and it's the correct one, so that's good. Alright, so AB problem, because it's a separable differential equation. And, the previous problem was also AB for the record. Just application of a derivative at a point. Actually, I take that back. It's a AB problem, the differential separable differential equation part, but this part right here is actually BC because partial fractions is a BC topic. So you might see a problem of that same nature on the AB part, but you wouldn't have to do partial fractions. It would be easier to get the antiderivatives and so on. So that's that wouldn't show up on just the AB only test, but one like it might. What else? Alright, and again, on 45 we got a line that we don't know the slope and y-intercept for. Says we just got this line y equals mx plus b. B is greater than 2, it says, however. It's tangent to the graph of this parabola at a point in the first quadrant. And the question is, what are the possible values of b? Okay. So, keep in mind that the picture of this parabola, it's got 2 to the right and 2 up for the vertex. It's in vertex form, so we can do that. We can see that the zeros here are going to be 2. No, not 2. If I put a 0 in for x here, actually I get 0 in for x would give me 4, negative 8 plus 2 would be negative 6. So that means that 4, negative 6 would be another point in here. So ultimately I would have the shape. Alright, and the question here says that if I have a line that is tangent to this graph and has a y-intercept of b greater than or equal to 2, keep in mind that means that the line would have to go through 0, 2, or something higher than it. True? So if it went through 0, 2, okay, could I have a tangent line here? Sure. Those two are horizontal to each other. So that means that ultimately, again, the question is what are the possible values of b? Okay, we could have a tangent line of b equals 2. That would be okay. It would be horizontal there. Question is that the only one? Or could we have a tangent line that maybe did something like this? Okay. Would there be another possible tangent line with a higher b? Seemed like it would make sense in our crappy picture, right? Okay. So the question is, how can we tell? So again, keep in mind, what does it mean for a line to be tangent to a curve? It means that it not only touches the curve in one particular spot, right, but it also, the line and the curve have the same derivative, the same slope, I should say. So let's keep that in mind. And knowing that our function that they gave us is negative 2 x minus 2 all squared plus 2, if we find the derivative of that, negative 4 times x minus 2, which ultimately would be negative 4x plus 8. True? Alright. And so, with that, the question is then, if this is our derivative at any given point, okay, we know that the derivative at 2 is 0. That matches up with our derivative here at our maximum point. True? Just for argument's sake, if we were to just say, what about the derivative at 3? The derivative of 3 should be negative 4. If I put a negative 3 in here, or a positive 3 in here. So if I got a slope at 3 of negative 4 here, okay, and ultimately I draw my line as such, and I run out of space doing this, but bottom line is if I were to draw my tangent line there, okay, I mean, I could certainly draw a tangent line there, and ultimately wouldn't it in fact cross the y-axis at some point? And if it does, let's see if we can figure out where that is that it crosses the y-axis. Okay? So again, keeping in mind that the line that we've drawn here would have y minus 0 and then negative 4 x minus 3 for the equation. To give us y equals negative 4x plus 12. True? So that particular line at 3 itself, it would have that as its y-intercept. So ultimately we could see a 12 there. So what does that? That essentially rules out letter B. It only goes from 2 to 10, it says. Alright. And ultimately, let's see what happens just for argument's sake if we did the 4 here. If we did y prime at 4, we'd have negative 8. True? So we'd have negative 8 there. And so if I at 4, which is way down here somewhere, bottom line is if I were to write an equation for the tangent line for this curve at that point, the point itself, a 4 in here would give me 2 squared would be 4. Negative 8 would be 6, like we said. Right? So it would be y plus 6, and then x minus 4, and then our slope would be negative 8. So if we did y plus 6, we did negative 8x plus 32. And we subtracted 6, we'd have negative 8x minus 26. Plus 26, sorry. Alright. So, with that, that would be our equation. And again, this is going to continue to decrease, okay, which it is. It's going to continue to decrease. We could continue to draw these lines that are tangent here. And when we read the question again, it says, so this line that has a b value greater than or equal to 2, it's tangent to this graph at a point in the first quadrant. Okay? So ultimately, what's the problem with this line that we just found here? Where is it tangent to this curve? Is that the first quadrant? So where's the furthest we can go here down? It would be that point would be the furthest we could go, wouldn't it? If we went any further than that, we wouldn't be in the first quadrant anymore, would we? Okay. So again, it specifically said that the tangent line has to be tangent to the curve in the first quadrant. Okay. So ultimately, how far could we go in terms of, this would be essentially our limiting tangent line, wouldn't it? So therefore, it'd be from 2 to 12 we could use, which would be the C choice. Okay. And you'll notice that that they didn't include 12 there. How come? This point I have circled, is it in the first quadrant? That's, who remembers the name for a point that's on the line? Oh, bonus points today.
Inner quadrant.
No. So a point that is on one of the axes is called quadrantal. All right. Okay. Any questions on that one before we carry on?